everyone. This video is going to be a proof of the product rule. So that derivative rule that we've been using in class, we're going to do an algebraic proof of it here. So we're going to need the limit definition of a derivative, which is the limit as h goes to 0 of capital F of x plus h minus capital F of x divided by h. And in this particular case, I am setting capital F of x equal to lowercase f of x times lowercase g of x. So that is my product. Just before we get started, this whole proof relies on adding a fancy zero. So this kind of algebraic trick is used in things like completing the square, where you add and subtract the same value, but it gives you some nice algebraic simplification. So we'll see what that fancy zero is going to be in a moment, but that is the whole kind of basis of this proof. So I'll start with my limit definition. The limit as h goes to 0, and we're doing f of x plus h, g of x plus h, there's the product, minus f of x, g of x, all divided by h. So my fancy zero here, which I'll write in orange, I'm going to subtract first. It's going to be f of x plus h times g of x plus f of x plus h times g of x. So where this particular fancy zero comes from would have to come from a lot of practice. If you did a bunch of examples of a limit first principles definition of a derivative of a product of functions, if you did that a bunch of times, you would probably be able to find the pattern eventually. In our case, it's just going to show up and it's going to be a little bit magical. So I'm going to insert that into my numerator. If I add 0 in the numerator, I'm not really changing anything, so that's why it's okay. So I'll have f of x plus h times g of x plus h. Now I'm going to start with my fancy 0, which I'll use in orange again. F of x plus h times g of x plus f of x plus h, g of x, back to blue, minus f of x, g of x, all over h. Okay, so now I'm going to be common factoring. So I'm just going to split up my numerator so I can see kind of a left and a right-hand side. And I'll continue my limit. And if I'm common factoring in the first two terms, the thing I have in common there is f of x plus h. So once I common factor that out, there's going to be a g of x plus h minus g of x portion to it. And now when we get to the right-hand side, the thing that's in common is I have a g of x. So I'm going to do a plus g of x. And what's left, if I common factor out, is f of x plus h minus f of x. And this is all over h. So what you can kind of see what's left in the brackets there, we have a g of x plus h minus g of x. That is the limit definition for the derivative of g. And on the other side, we have f of x plus h minus f of x. That's going to lead to the limit definition for the derivative of f, lowercase f. So as we continue here, we're going to split up this fraction. And with a limit property, we can separate this into two separate limits. So we're going to have one limit here as h goes to 0. And we'll have f of x plus h. And then we'll have over h. I'm going to simplify this here a little bit. Let's make a big set of brackets. And we'll say that this is g of x plus h minus g of x all over h. Here's the first part. And that is the limit definition for the derivative of g right there. And then we have plus g of x. And same sort of thing, I'll use brackets here, f of x plus h minus f of x, all divided by h. Since these two are being multiplied together, I can attach the h in the denominator to either one. If we expand back, we'll get back to the original. So now the limit, as h goes to 0, we can apply this limit property throughout. So we'll get actually 4 separate limits. So we could say the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of my square bracketed term, g of x plus h minus g of x over h, plus the limit as h goes to 0 of g of x times the limit as h goes to 0 of f of x plus h minus f of x. So that's just the limit property, kind of expanding through, or almost distributing through the different versions here. So as the limit as h goes to 0 gets applied, as h goes to 0, this first part here will work out just to be f of x. This second part here, this is g prime of x by definition. Then there's no h even in this third one, so that is just plus g of x. And then the last one, that is the limit definition for f prime of x. So there we have the product rule. So we could finally conclude, we can say like, therefore, capital F prime of x is equal to f of x g prime of x plus g of x f prime of x. So there it is, start to finish. All depends on that fancy 0. There's one other way we can look at this, and this is a bit more hand-wavy, we'll say, but it is visual. So any product can be seen, with an area. So we've got a couple of things here where we've got f of x and g of x. That is represented here as their product. So this is the part that eventually gets taken away in the limit definition of a derivative, because you do f of x plus h times g of x plus h, but we minus off the f of x times g of x. So this part here will be all gone when we subtract. So really the derivative is coming from these other 3 areas. Okay, so we've got this area here in orange, which we're going to focus on. And the other 2, so we have g of x times df, which is like the change in f. So that would be like g of x times the derivative of f. And the other part on the bottom right is f of x times dg. So that's like f of x times the derivative of g. So those 2 are the parts that kind of live on in the formula. So this part in orange is the part that goes away. So as h goes to 0, this is kind of the hand-wavy argument, is that as h goes to 0, each of these 3 remaining blocks will eventually get to 0. But this orange block here, this will go to 0 much faster than the other 2 blocks, right? The df in this top block up here, this df will make that block eventually go to 0 as h goes to 0. This dg will eventually make this block go to 0. But when we multiply df and dg together, that will make this block go to 0 kind of quadratically. And so it just is much faster than the other ones, which would kind of go down linearly. So if the if this part in orange is kind of negligible and the part in blue is removed because we subtract it in the limit definition, then the only parts that remain for the product rule are here. So this is kind of a visual alternate definition for the product rule proof.